Okay.
It's my pleasure to introduce our next speaker, who's Rowen. And he will talk about the structure of axial algebras.
Thank you very much. It's a pleasure being at this conference. I think I'm the most, latitude here of anybody who's present. David has more in general. I was trying to think for a long time how this has anything to do with the Brauer group. And I came up with a wonderful explanation. Who was the best researcher in the Brauer group? I think maybe Albert. And if it wasn't Brauer, it was Albert. And he started the subject in the 40s. So anyway, let's see what I can do here. Oh, now it's stuck again. Oh, my page down maybe? Oh, it's stuck. Okay, I'll try this. So A is going to be an algebra, which is not necessarily associative or commutative, and with the multiplicity union. And everybody knows what an idempotent is, and the 0 and 1 are trivial. So the role of idempotence is very important, since the thing appears to be composition of an associative algebra. There's probably things before that. Now we're going to define, I'll take this up. We're going to define the left and right multiplication maps, and their eigenspaces, and denote them A lambda of LA and A lambda of RA, because they act on the left and on the right. And from two sides, we're going to define the intersection. So this is more terminology. When lambda equals delta, we'll just write one subscript. And here are two very important instances: the right and left annihilator, and the 1 contains A always, so it's not non-empty. So if you have a algebra A, you have and an associative algebra, you have this. That's the Pierce decomposition. And if the non-associative case, as I said at the beginning, goes back to Albert, who proved for Jordan algebras that you have three idempotents. A1, or the three eigenspaces, the 1, the 0, and the half. Maybe the 0 is trivial. But he also proved more. He proved that you have certain rules when you multiply eigenspaces. And okay, this is in his paper, but for Jordan algebras, it's much simpler. So Albert's theorem shows that A is a graded algebra with respect to its eigenvalues, the eigenspaces. Now, nowadays, we call this a fusion rule. And it's simply mapped from a component and another component to a sum of components. So this is typical fusion rule. So the fusion rule is symmetric if the algebra is commutative. I just want to throw in that you could think of this as a hypergroup multiplication, if anybody's interested in hypergroups. Now, the Pierce decomposition now reads like this. We could just look through the different things, where the empty set means it's 0. If you have any questions, it's hard for me to see you, so please just talk out. The fusion rule for commutative power associative algebras is this. That's what I wrote before. And for Jordan algebras, it's simply this, that the product of two components is always a component, except the half times the half is the 0 component plus the 1 component. So that's still not enough to say much. So we talk about semi-simple idempotence when the left and right multiplication operators are semi-simple. Okay. And an axis is a right and left semi-simple, right and left and right semi-simple idempotent, for which the right multiplication commutes with the left multiplication operator. So A x A is well defined. Okay, well that's an axis, and an axial algebra is an algebra generated by axes. Okay, so the most famous example is the Jordan algebra. So now we can decompose any element in terms of its eigenspaces in A, and that we call the decomposition, of course. And since, because of this, you only have, y lambda I delta j will only take on a limited number of values. So here's some more history. Albert brought this in with his 1948 paper, which was amazingly modern, although the terminology, of course, was not. And Paul Rehren and Spectorov resurrected this, which had sort of become dormant, because it had ties to the Greece algebra and the Munster group and Majorana algebras. So some of them have two eigenvalues other than 0 and 1, like the Majorana algebras have a quarter and a 32nd. And okay. And if you're interested after this lecture, read the article of Spectorov. It's a wonderful article. Now, so if you have only one left eigenvalue and one right eigenvalue other than 0 and 1, then you have this. And this is the simplest non-trivial case. So we're going to call this a lambda delta algebra. That's lambda to this stuff. Okay. And the grading, oh, yeah. So the decomposition now, there are 9 possibilities. And that's, I don't know, that might be too much to study reasonably. We haven't been able to get very far. So we put in another axiom, which comes from Jordan algebras, that first of all, we say that it has decomposition Z2 cross Z2. Okay. We'll say that has type lambda delta. But we're going to go further, and we're going to say that the axis is type mu j, mu, where mu and nu are in these two sets. If A is a direct sum of 3 eigenspaces, and even this is pretty complicated. So this is by far the simplest instance of what's going on. Okay, so we'll say that has Jordan type. So that's still not enough. So we say that A is weakly primitive if the one eigenspace of A is Fa, and A is primitive if both the right and the left eigenspaces of A are Fa. And HRS dealt with commutative algebras, so weakly primitive and primitive are the same thing for them. Okay, so a weakly primitive axis cannot be the sum of two smaller, or not the sum of two smaller axes, because there's only degree 3. So the on the other hand, the matrix unit E11 is weakly primitive in the matrix algebra MNF, but it's not primitive. That's okay. So the main idea of what we wanted to do is we studied these axial algebras of Jordan type. Actually, we started with primitive algebras of Jordan type, and then went on to weakly primitive. And so let's see, if you have a primitive axiom of Jordan type, you have to have these two things at 0, because if you multiply on the A on the left, you're multiplying by something that's not 1, and when you're multiplying on the right, you're also multiplying by something that's 1, not 1, and they're two different things. So so A lambda delta is A1, well, I'm saying this wrong. What I wrote is the correct thing. The lambda 1 and the 1 delta eigenvalues are 0. We also want this. This is less obvious, and we proved this in 2 papers totaling about 25 pages, where in the first paper, we proved that the dimension of A and B, of the algebra generated by A and B, is less than or equal to 5. You see, at the outset, it's less than or equal to 6, because I'm sorry, it's less than or equal to 7. And then we got down to 5, and then we saw that the 5 case and the 4 case doesn't exist. So we're down to 3. Okay, so WPAG will be a weakly primitive axial algebra, and PAG will be a primitive axial algebra. And this is the decomposition. And we'll say that X is type lambda delta if each primitive axis has this type. There's nothing that says at the outset that all the axes have to have the same type. And so another type that comes up all the time is the complementary type, which is 1 minus lambda and 1 minus delta. And these can come up. Okay. So here, Rowen and Spektorov, they took commutative, they only had 1 extra eigenvalue, and they also have the stronger fusion rule that A0 squared is an A0. And it turns out that, I said that for primitive axial algebras, this is true. And the stronger fusion rule you can prove. not for every single axis, but you can prove that you have a generating set of axes such that this happens for every axis in that generating set. Okay. And just by the way, Albert came up with a commutative power associative algebra failing this. So you have to be careful. Okay, so our project was to put this theory into a more comprehensive framework, which has some interesting new examples, which I hope I'll get to. Okay. So we'll deal with the non-commutative setting, which is flexible, that you have to prove. And it turns out that the non-commutative part of A is a direct summand, and we can characterize those. So we can just remove that. And so that brings us back to the commutative case. And as I said, in a primitive axial algebra of some type lambda, the type is unique. It's either lambda or 1 minus lambda. And if you choose it correctly, well, actually, you can always choose between -1 and 2, if they're both of them, and you choose 2. And then if A has type 2, then this will be true. For type -1, it's open still. Okay, and then we get a Frobenius bilinear form, which is unique up to the choice of these lambdas. And then we tackle the finite dimensional question. Where am I? Quarter to 4? So now when you have only one extra pair of eigenvalues, then you have a Z2 decomposition. If you have many pairs, you could have Z2 cross Z2, and it works, but it's a mess. And so, so I'm just going to talk about the case where you have one extra eigenvalue, which you write y is y plus y minus, let's see. Okay, so you write y equals y plus y minus for y plus being the sum of the 0 and 1 eigenvalues, eigenspaces, and y minus being in the lambda delta eigenspace. And then since this is a 2 grading, it's very easy to check. Then everybody who's ever worked in group algebras probably knows that this is a automorphism of degree 2. We just switched the sign of the extra component. And but Miyamoto sort of discovered it independently, and so they're called Miyamoto involutions. Even though it's not really an involution, it's really an automorphism. So, but involution in the group theoretic sense. So, and then either these commute, these all have order 2, right? Because look at this, it has order 2. So any group generated by elements with order 2 is a dihedral group. So, so you get the dihedral. And so, okay. So CL of X is the set of X to the tau, where tau is a product of Miyamoto involutions. So tau is in that group, generated that dihedral group, and X tau is what's written. And there's a very important theorem that if A is generated by a set of axes of Jordan type, then A is spanned by them, or by the image of all the axes under these evolutions. Oh, let me just say that y to the tau is an axis, if y is an axis. So you take all of them, and then they span A. And as I said, if you don't, if even in the more general case, you have the same sort of thing, but you have 3 near-motive influences because the group is Z2 plus that group. Okay. So I just want to repeat, since it's so important, that any algebra generated by a set of axes having a certain property also is spanned by axes of that property, namely the Miyamoto influence. Okay. Now, so an NPAG will be PAG generated by n primitive axes. And so if it's generated by n primitive axes, it will be spanned by many more than n primitive axes. And that's probably the major question in the subject. How many axes do you need to span an n-generated axial algebra, primitive axial algebra? Okay, so let's look at an example. So we look at the sum of axes where any 2 axes multiply in this way and generate a 2-generated algebra. And that is the axial algebra. And in fact, all the idempotents are axes of the same type, of type lambda delta in this algebra. Oh, excuse me. That's only true if lambda plus delta, if this is true. And this, you can just check, means that lambda equals delta, you have the commutative case, or lambda plus delta equals 1. If you don't have one of these 2 cases, you don't get axes. Okay. So, and then the Jordan fusion rules. Oh, in the first case, the Jordan fusion rules say that the extra axis is a half. In the second case, you get something for any lambda. You can take delta equals 1 minus lambda, and then you get a primitive axial algebra, which has dimension n, as I said. Okay. For lambda equals 1, okay, so I didn't say these have to be not 0 or 1. I mean, they can be, but not 0 or 1. But then you won't get the fusion rules. You lose the fusion rules. Why? Because lambda equals 1, we get a what do you call it? Left nilpotent band. AB equals B. So A is not primitive, and B equals A. So it's the left band. So suddenly we have the left band. If we forget about lambda plus delta, but you lose the fusion rules. This algebra does not satisfy the fusion rules. In fact, it's associative, right? It's a semi-group algebra. It's associative. Okay. What about the right regular band that Guy talked about? Well, you get this 4-dimensional algebra spanned by these for n equals 2. But it's not weakly primitive because xi is not primitive. You have 2 things not in its one eigen, not in xi, which is its one eigenspace. Okay, so every primitive idempotent is an axis, I think I mentioned that, of the same type. And you can actually state what the primitive axis are. And this is which is defined here, a square zero ideal. Okay. So that's sort of strange because the axes span the algebra, but you have other elements in the span, other important elements which are not axes, which are square zero. Okay. And in fact, A is a local ring. You mod out the radical and you get fxi plus fxj, or the direct sum of all the fxi's. Okay. I think I'll skip. Well, here go over the proof quickly. So if A is x1, then xj squared will be xj, which will be this. And actually, maybe I shouldn't sketch it because this is delta xi plus lambda xj. That should be a lambda. And this is the square, this is the square zero ideal, written in a different way. And you see, this proves it's square zero. And since it's square zero, you get the Jordan fusion rules because you can't wind up with a non-zero eigenspace. Yeah, when you take the product of those two. Okay. So, and then I checked when the idempotents are, when the elements are idempotent, and you can see that, work it out with the axes. Okay. So I started talking about two-generated algebras, and what's true in this subject, and in fact, is the only algebra that HRS deals with, are the two-generated algebras. Because if you have let's just say it. If you have an axis, a product of two elements, each element is spanned by axes. So by distributivity, you have the sum of the products of pairs of axes. Each pair of axes generates a two-generated axial algebra. So if you know all the two-generated axial algebras, you almost know everything. Although we'll see that that's a very dangerous statement. Okay. So here's a theorem for two-generated, two-dimensional algebras. You get what we had before. Okay. But incidentally, if you have one is equal to lambda plus delta, and one equals lambda prime plus delta prime, and they're not equal, then you don't get then you don't get the fusion rules. But if they are equal, then you get the fusion rules. Okay. There's one more important two-generated algebra, which we're going to call this x squared. Oh, great. That's a squared. A squared equals a. B squared equals b. Y squared equals 0. And AB is lambda times y, which is a whole bunch of other products. And BA is delta times y, which is equal to a whole other bunch of other products. Where delta is 1 minus lambda. And in this algebra, A lambda delta is Fy, which is a square zero ideal. And A0, I should have written A0, is F times B minus Y. Okay, so that's an algebra. And in fact, any weakly primitive algebra of Jordan type is one of those. What did I write down here? No, it's not going to be. Maybe it's not B. Okay. I don't know what. Maybe it's certainly not B. That's AB, and that's BA. And here you go, delta equal that. Okay, so, okay. So as before, this is a primitive axial algebra. Lambda is not equal to 0 or 1. And it can be generalized to produce more. Now, this can give you the left regular Jordan band. I mean, left regular band. Before we had the left nilpotent band. Here we have the left regular band. Because AB is Y and BA is Y prime. And you can budget so that those are idempotent. If you don't have 0 and 1. Okay. And there's only one of the idempotent. So all the idempotents have either type lambda delta or type delta lambda, except the unit element. This is the proof of that. And you can get more algebras also. But those are the only PAJs generated by 2 elements. The ones I just did are the ones of dimension 3, and the ones I did before are the ones of dimension 2. Yeah, A, B, and Y. Okay. And if you switch A and B, you get an honest to goodness anti-automorphism, which I couldn't refrain from saying. Okay. Then you switch A and B. That gives you the definition. Okay. Now, so now we know the basic examples. What can we say about algebras generated by more than 2 axes? Well, it's complicated, but there's a very nice graph that you put down. It's like almost like the commutative represent. Its vertices are the axes, or the Miyamoto images of the axes, and you have an edge whenever the product of 2 axes is not 0. So if you have the product of 2 axes equal to 0, then you just have F times F. So this gives you a chance of avoiding F times F. Okay. So if X is primitive of X of joint type, then this is actually an undirected graph. If you have X double prime equals 1, and X double prime or X prime equals 0, you have something different. That the graph is directed and not undirected. And so we can talk about the components. And if you have any 2 primitive axes, then A times the image of B under the Miyamoto involution is not 0, or B times the image of B is not 0. So you have the distance is at most 2, because you can go from A to B tau A. Okay. Any component that is closed, that's not trivial at all. And here, wait a second. No, a component, no, that is true. I'm sorry. It's clear that any component is closed. But suppose you have a set of axes and the Miyamoto set, and AI is generated by the axes. that should be the Miyamoto axis. Then A is the sum. Wait a second. No, I don't have to have that. A is just, it's just AI is generated by the components, by the closed components. And A will be a sum of the AI. And AI, AJ will be 0 for any I not equal to J. But AI intersect AJ need not be 0. It annihilates A, but it doesn't have to be 0. And if you have sum in different components, then each of the yi annihilates A. And this is enough to prove that the commutative components are direct summands. And the non-commutative components are direct summands, and the commutative components could sort of fit together. So as I said, we can get rid of the non-commutative cases. And I said that there are examples. Okay. And okay. So you can have, if all the axes are generated by non-commutating axes at the same time, then you get a direct product. I think, and I said before that you could have this case. And it's very interesting that you get it. So we have all the non-commutative ones. And this gives you a complete description of non-commutative axial algebras. And you'll notice that if you read through this, this is finite dimension, this is finite dimension, and this is products of these two. So this is finite dimension. So A has finite dimension. If A is a non-commutative axial algebra, then A has finite dimension. I put that down here. I can't do it's 410 now. Okay. So we have in this theorem that the products, so we take the axes of type lambda delta and the axes of type delta lambda. And the products of, so they are complementary type, and the products we call Y. And I said Y is the radical, algebraic radical of the algebra. Y is equal to 0. For X connected, we have that. If you take these to be maximal possible, which means you apply all the Miyamoto involutions to them, then you get precise equality of the dimensions. And A is no annihilating element. Okay. Next, what about dimension 3? Primitive PAJs, primitive axial algebras of joint type of dimension 3. Well, HRS took A and B to have the same type. But you could conceivably have A have type lambda prime and B have type lambda. And then they have conjugate type. Okay. And if lambda is a half, then everything's a type half. Because, right, you get 1 minus a half is a half. And then you can define sigma to be this element. And this element plus A and B generate A. And this gives you the multiplication table. And therefore, let's see. Well, we have three cases. If sigma is 0, then you just have the two-dimensional case. We don't have sigma. If sigma is not 0, and sigma times A is 0, and sigma times B is 0, that's a very strange case. Then sigma is in the radical. Okay, and otherwise, you have a unit element. Now you have a unit element, and you can prove that you either have A and B having the same types or complementary types. If A and B have the same types, then you have the algebra, the HRS algebra. And if they have different types, you get a different multiplication table with isomorphic as an algebra. Okay, next. Define the projection of A onto the space generated by A. We'll call that phi A. So you have three possibilities. Three possibilities where they're all the same. We want phi of A of B to be phi B of A. But in the -1, 2 type, which I mentioned before, that's false, and that's a pain. Okay, but you can always choose B to have type 2. You can throw out the axis of type -1, and you generate the set. And so this is what a Frobenius form is. It's a bilinear form, which is associative, and it's normalized with A equals 1. And so the theorem, which essentially Spektorov and Yoav proved, although we proved it a bit extension, is that it has a normalized Frobenius form, which is unique up to the choice of your generating set. And this is how you get the projection onto the A axis, gives you the coordinate of the Frobenius form. And let's see. So since we keep on getting stuck with this -1, 2 situation, we should notice that the -1 axes are never anisotropic. If they have a 2 axis in the same connected component, they're always isotropic. Okay. So every PHA is a finite direct product of connected non-commutative PHAs and one commutative PHA. Every PHA is flexible, and A naught squared of A is equal to A naught of A for any primitive axis of joint type -1, which we can arrange. Okay, so those are the three main structural theorems. But we still don't know actually the -1, 2 case. The three-dimensional case we know is true, that this is still true. But the three-generated case we don't know. Okay, so when do primitive axes have Jordan type? This is a very serious question because, see, suppose we have an axial algebra and we take it as a primitive axis. We want to know whether it has Jordan type, because then we can we can take the algebra generated by any three primitive axes, and if two of them have Jordan type, the third one has Jordan type, and then we get a very nice. Then we get it that it satisfies the the fusion rules. So in other words, if we can prove this, then axes. And you see, this is what I said here. If you have two axes, you get the fusion rules. If you have three axes, it's not who you get the fusion rules. And it's an exercise to see that if the fusion rules work for any two axes of joint type and a primitive axis, not necessarily of joint type, then they work for any situation at all. And so we've been working on that for a long time. Again, okay. This will show that A has joint type probability. And the last question is, what about finite dimensionality? Any two generated axial algebra of joint type has dimension 3. That's pretty low. What about a 3 generated axial algebra? Well, that was open for a long time. Oh, before I get to that, if you have type not half, then Hall, Rowen, and Spectorov proved this using, I think, the classification of 3 transposition groups. But that's not very satisfactory. So people have been trying. I mean, it's a wonderful illustration, but people are sort of hoping that they do much better. So Koshkov and Starletov proved that the 3 generated CPAGs have dimension less or equal to 9. And the base is very simple. A, B, C, A, B, A, C, B, C, A, B, C, B, A, C, C, A, B, if you put in the parentheses. And so we've been working on trying to generalize the proof to 4, and it's difficult. It's very interesting. And maybe the last thing to talk about is that if you look at the representation algebra A, then if that is finite dimensional, then the representation, then the algebra of A is finite dimensional. So you can work on that, and that's an associative algebra. And so it seems much more likely that that will be a possible direction. Thank you.
Any questions? Questions at this point?